When physicists can't sleep at night, they turn their attention to some of the most fascinating and yet perplexing topics ever to enter the human mind. I'm talking, of course, about guts and toes. No, I'm not talking about those guts and toes. I'm talking about a grand unified theory and a theory of everything. These two ideas are different ways to try to achieve the ultimate goal of physics, which is to try to devise a theory that can explain all physical phenomena from a set of simple and fundamental principles. While this has long been the ultimate goal of science, the first modern step forward was taken in the late 1600s. Sir Isaac Newton was one of the most brilliant people ever born, with the invention of calculus and his laws of motion being just two of his achievements, either of which is worthy of granting him scientific immortality. However, perhaps his most impressive scientific accomplishment revealed a deep connection between the steady pace of celestial bodies marching across the heavens and the slapstick comedy of a person slipping on a banana peel. This guy always cracks me up. Basically, his insight was that the gravity that governs matter here on Earth and the astronomical world we see in our telescopes was the same thing. Well, this seems obvious to us now. It really isn't. During Newton's time, some theologians still claim that the planets move because they were pushed by the beating of angels' wings, and the scientists of the era were guided by Aristotle's explanation of gravity as objects wanting to move to their natural place. These two phenomena could easily have had different origins. Modern scientists have a term that describes Newton's achievement. We say that Newton unified celestial and terrestrial gravity. Instead of two phenomena, both sets of observations could be explained by a single principle. An even more impressive example of unification was accomplished in the 1860s. Before that date, some scientists studied the behavior of magnets and compasses, while others were fascinated by electricity. Although a few experiments had been performed that revealed an interplay between electricity and magnetism, it was when James Clerk Maxwell wrote down what we now call Maxwell's equations that we understood that electricity and magnetism were actually just two facets of a deeper and more fundamental phenomenon called electromagnetism. Since Maxwell's seminal paper, electromagnetism has also been shown to be the origin of light and all of chemistry. His insight was very impressive indeed and rivaled even Newton's brilliance. Thus we see that the concept of unification, that is, the idea that seemingly disparate phenomena can have a common origin, has an illustrious history in physics. Naturally, scientists wonder what the next big unification will be. In an earlier video, I described our modern understanding of the universe. We physicists call this the standard model of particle physics. In this highly successful theory, we identify four, or by some accounting, 5 distinct forces that are needed to explain our world. These are Newton's gravity and Maxwell's electromagnetism, but also 2 new forces called the strong and weak nuclear forces. These forces only have a significant impact at a very small distance scales, more specifically for sizes smaller than a femtometer. A femtometer is approximately the size of a proton. Some scientists also would identify the recently discovered Higgs boson as the signature of a 5th force, specifically the interaction that gives mass to fundamental particles. Indeed, the story of the Higgs boson is part of the tale of the most recent successful unification of forces. In the 1960s, physicists demonstrated that electromagnetism and the weak nuclear force were actually a single phenomena, and the Higgs boson is the reason why the two forces seem so different. The term for this joined force is the electroweak force. Naturally, scientists wonder if the seemingly independent remaining forces, gravity, the strong nuclear force, and the electroweak force, might actually be different manifestations of a simpler and more inclusive force. There are reasons beyond the historical example to speculate that this hypothetical unification is natural. For instance, if we look independently at the strong, weak, and electromagnetic forces, we find that their strength depends on the energy at which we study them, with some getting stronger and some getting weaker. In a most provocative coincidence, the strength of the 3 forces becomes the same at a single energy. This energy is extremely high, specifically 10 to the 15th billion electron volts, which is about 100 billion times higher than we can study with the highest energy particle accelerator ever built. This technological wonder is called the Large Hadron Collider, or LHC. With perhaps a bit of scientific hubris, we already have a name for this hypothetical theory that unifies these three forces. We call this a grand unified theory, or GUT. There's been a lot of speculation about the exact form a GUT must have, but beyond the fact that the theory must explain how the electroweak and strong nuclear force are different aspects of a deeper theory, we really don't have a clear vision of what such a theory might look like. You'll notice that I haven't mentioned gravity in my description of a unified theory. That's partially because we don't have a good idea of how to write a theory of quantum gravity. This is different from the other known forces for which we've long known how to write in a quantum manner. However, we also have a name for a theory which incorporates all known forces. We call this a theory of everything, or TOE. While we also don't know what a TOE will look like, we do have some ideas about it. For instance, if there are no surprises, we expect that the energy at which all forces unify would be at what is called the Planck energy, which is about 10 to the 19th billion electron volts, or a quadrillion times more energy than the LHC can provide. Using the same technology that we use for the LHC, we need an accelerator with a diameter about 1,000 light years to study the collisions at that energy. So we're not going to be building that particular facility anytime soon. Of course, not being able to test the idea doesn't stop scientists from conjecturing what such a theory might look like. For instance, superstring theory is one idea which seems to be able to incorporate all the known forces, and there are some other ideas that also might lead in the right direction. However, the simple fact is that we're far from having either a grand unified theory or a theory of everything. When you get right down to it, we're not even 100% sure that either thing even exists. Physicists often say that we want to find a theory so inclusive and yet so simple that we can write the equation of the universe on a t-shirt. So I called in a few favors from some buddies over at the time travel division to get me a t-shirt from the future that sports the equation, and they did. Unfortunately, to preserve the timeline, they had to blur the equation. But no matter. My colleagues and I will eventually figure out what it says. And when that day comes, I hope you'll join me in wearing the ultimate expression of geek chic.